Hello, thank you for your interest in this presentation. My name is Fernando Resende. I am with the University of Texas at Tyler, and I'm presenting today on behalf of Jiaoying Li from Southeast University in China. This work is about catalytic fast pyrolysis of rice husk and waste greenhouse plastic foams, and it's a collaboration between Southeast University, the University of Washington, and UT Tyler. So let's start talking first of all about our feedstocks of interest here. The first one is rice husk. Rice is the third most produced agricultural commodity in the world. And rice husk itself is currently discarded just as an agricultural waste. It has a very small bulk density, meaning it's very expensive to transport even small amounts of mass. Therefore, there is interest in converting the rice husk into more energy-dense forms. The other feedstock is the waste greenhouse plastic films, which we're going to be identifying here by WGPF. And the greenhouse plastic films, they are used in food crops production. They provide protection from elements. They have good sealing and thermal insulation properties. And the WGPF is produced at a rate of 4.6 million tons worldwide. So it's an important resource that is currently just disposed by landfilling and incineration. So we see an opportunity there with both of these feedstocks. And the way we're going to be converting those into fuels is by fast pyrolysis. Now, fast pyrolysis is a thermal conversion method that uses an inert environment at high temperature, 500 to 600 degrees Celsius, with a very high heating rates and short residence times. Now, as a result of the process, we get normally three phases. There is a gas, a flammable gas, there is pyrolysis liquid oil, bio-oil, and there is char. Our focus here today is going to be on the pyrolysis oil, the liquid fuel that is produced. The bio-oil, the liquid fuel, though, has some characteristics that complicate its use or compromise its use, let's say, as a transportation liquid fuel. It has hundreds of oxygenated compounds, reactive functional groups like ketones, acids, alcohols, and those oxygenated groups they lead to a poor chemical stability. There's also high viscosity. The product is immiscible with crude oil. The heating value tends to be low compared to the energy content of fossil fuels, and it has high acidity and a very high water content. So if you look here at the Van Crevelen diagram, the hydrogen-carbon ratio as a function of the oxygen-carbon ratio, you see that the bio-oil stands here very high in terms of oxygen content compared to most of the conventional fuel sources. Now, there is a reason why we are interested in using both of these feedstocks here. The rice husk has a fairly small hydrogen content, but the WGPF has about twice as much. It has a significant content of hydrogen, and the hypothesis here is that the WGPF can work as essentially as a hydrogen source for the rice husk, and by doing so, it can promote the formation of hydrocarbons and therefore improve the quality of the liquid fuel obtained from fast pyrolysis. Now, not only we are going to do that, but we are going to be carrying out the process in the presence of catalyst. Catalytic fast pyrolysis, or CFP, consists on the deoxygenation of oxygenated volatiles over zeolites. And there are two ways in which usually this can be done: in situ, with the biomass and the catalyst essentially mixed together, or ex situ when they are in separate units. In this work, we're going to be focusing only on the CFP performed in situ with the biomass and catalyst together. Now, what is the catalyst here? We're going to be using AIChE, which is a microporous molecular sieve, which tends to be a very effective catalyst for catalytic fast pyrolysis. It has a strong acidity, so it has a good activity for the process, generating typically BTX products, okay, the aromatic hydrocarbons. Now, one of the issues, however, with AIChE is that it's being a microporous material, has very narrow, very small pores, which are about the same size as the molecules involved here, or the products of the reaction, meaning that there is a good chance that those products can plug the pores and forming coke and thereby deactivating the catalyst. Now, in contrast here, we also have another zeolite, MCM41, that's a mesoporous molecular sieve. And MCM41 is, because it has larger pores, doesn't face the same issues that AIChE has with coke formation and plugging. However, it doesn't have the same level of activity. It's not as acidic, so it doesn't promote the formation of hydrocarbons to the same extent as AIChE. So our thought here is that we would like to combine the characteristics of AIChE and MCM41, combine the pros essentially, in order to promote catalytic fast pyrolysis, the formation of aromatic hydrocarbons. So here we have the diagram of what we expect. We are going to mix rice husk with WGPF and a pyroprobe. And the thought here is that the AIChE is the core of the catalyst with an MCM41 shell. And then the pyrolysis should lead to aromatics and also aliphatic hydrocarbons. That's the general hypothesis here. The idea is that by doing so, we would help cracking the larger volatile molecules, preventing coke formation. So here we have our results. And what we see is on the left here is the products from WGPF. And this is all, first of all, this is all without the catalyst. Okay, this is prior to using the catalyst. The two plots on the right here show results obtained with the rice husk. Okay, now on the left you see that, so this is expressed as a function of temperature, but the main point here is that there's an increase in the total area obtained in the GC products when we increase temperature for the WGPF. However, for the rice husk, there is a maximum, because the volatiles, the oxygenated volatiles, at a certain point, if you increase the temperature past 600 degrees Celsius, they start to crack, decompose, forming gases. As it's shown here, we measure the amount of carbon dioxide produced, and it keeps just increasing with temperature. But the bottom line is the WGPF, as we perform the fast pyrolysis, it provides mostly hydrocarbons. And these are aliphatic hydrocarbons that are originating from this feedstock. In contrast, the rice husk is primarily, the products are primarily oxygenated materials. There's just a little bit of hydrocarbons, but only a 4.9% relative content here. We are defining relative content as essentially the size of the peak area for one specific product divided by the total product, the total area obtained by GC analysis. Now, what we do next is we take the two feedstocks, and prior here we shown the pyrolysis is happening separately. Now we are mixing them together at a ratio of 1:1 and performing the pyrolysis still without a catalyst. And the goal here is to verify the possibility of synergy between these two feedstocks. Now what we see is that the trends here, they are very similar to what we already observed for the WGPF. So the WGPF tends to dominate the results. and leading to a continuous increase in the yields of products, yeah, even at temperatures as high as 700 degrees C, and hydrocarbons, still aliphatic hydrocarbons, being the main products. Okay, so the WGPF strongly influences the products when it's mixed with rice husk. And here we are looking at essentially the same results in the form of a table. The only difference is that now we are looking at the possibility of synergy. On the first column here, what you see are the peak areas obtained when we do the pyrolysis of rice husk only. Second column, these are the peak areas when we do WGPF only. And the fourth column here, the last one, we are essentially just calculating an average, which is this is what we should expect to obtain if we are mixing those two compounds at a 1-to-1 ratio, keeping the total mass. Okay, the experiment that we report here in the column 3 is exactly this: is rice husk and WGPF mixed, and how the peak areas change with temperature. And what we see, so this here is expected, and this is what we obtain when we mix the feedstocks. And what the results show is that the peak areas for this mix of rice husk and WGPF is always higher than what we would expect when we just do an average of the experiments with the individual compounds. And what this is telling us is that there is a great likelihood here of synergy between the two compounds. Essentially, when you're mixing them, the final result is greater than just the sum of their parts. There is interaction between them, leading to a greater yield of products. Now, what are these products? That's what we are looking at here at the next slide. And what we see is the combined, so the results here for the mixture, they're all in terms of oxygenated molecules like acids, esters, ketones. They're always smaller than what we expect when we are just doing the feedstock separated. The exception here is hydrocarbons. So you see, we would expect 34% as looking at the two feedstocks separately, but we get 47%, a significant increase in reality, again suggesting a strong synergy between the two feedstocks. And our hypothesis again is that the WGPF is providing hydrogen atoms that promote the formation of hydrocarbons. Now, all of this is without the catalyst. Once we put the catalyst in, we continue to promote the formation of hydrocarbons. In this case here, aromatic hydrocarbons as opposed to aliphatic hydrocarbons. The total peak areas, they are higher in the presence of the catalyst, resulting from the catalytic activity. There is a maximum in the content of hydrocarbons at 600 degrees Celsius, and the yield of oxygenated compounds in the presence of the catalyst decreases significantly. Now, the results are shown again for the mixture in the presence of catalyst, now with varying ratios of rice husk with the WGPF at 600 degrees Celsius. And what we see is that the maximum peak area is at a ratio of 1 rice husk to 2 WGPF. When that ratio is 1 to 1.5, then the relative content of hydrocarbons reaches its maximum value, 17.1. The oxygenates go through a minimum as well at the situation 1.5. The relative content of the carbon dioxide is higher when the catalyst is present, suggesting the occurrence of deoxygenation reactions with the AGSM5 MCM41. So here we have our overall reaction pathway that we hypothesized and we confirmed based on the results. The rice husk and the WGPF, they interact. The WGPF by itself, pyrolyzing, can already provide aliphatic hydrocarbons, but it also works as a hydrogen donor that interacts with the rice husk in the formation of the primary volatiles from pyrolysis. Those volatiles, the large oxygenated chemicals, they react at the shell MCM41 callus, and then the smaller molecules, they can enter the pores of the AIChE with a stronger acidity to participate in the hydrocarbon pool, leading them to aromatics and gases. So here we have our conclusion is that the callus, the AIChE MCM41, changes the selectivity of this mixture, going from aliphatic hydrocarbons to aromatic hydrocarbons, and also increasing the overall amount of hydrocarbons. The WGPF, we saw evidence here that it actually works as a hydrogen donor to the rice husk. There is a synergistic effect, and within the conditions that we evaluated, the recommended temperature is 600 degrees Celsius, and the recommended ratio rice husk WGPF is 1 to 1.5. So to finalize here, we would like to acknowledge the sources of funding: the National Natural Science Fund Program of China, the Scientific Research Foundation of Graduate School of Southwest University in China, and the Program of China Scholarships Council. So that's it. Thank you for your attention. I appreciate your time.